pleasure to introduce Tanio Diaz-Santos, who did his PhD at the CSIC in Madrid. Afterwards, he continued to be a postdoc at the University of Greece in Greece and at the SPECTRAL Science Center at Caltech in the US. Then he was a fellow, an ALMA fellow at the University Diego Portales in Chile. And currently, he is an associate researcher at IA4 in the Institute of Astrophysics in Heraklion in Greece. So, please,
thank you very much. Well, first of all, I wanted to thank you all for being here and the organizers for inviting me for this seminar. It's been a pleasure, and I'm very glad to be in Lisbon. We were discussing during lunch that both my grandparents are from a place very close to Portugal from the north, and also from the parents of my mother from the south, from Leon. So we were visiting when I was a child, Braganza and Ribera do Douro, all the area around. So anyway, so today I'm going to be talking about the interstellar medium of the most luminous galaxies, near and far. And I want to start by introducing and giving you a little bit of context of why we care and why should we care about luminous infrared galaxies. And this is because these galaxies are a key galaxy population across all cosmic times. And basically, in a very summary and in a nutshell, basically, luminous and ultra-luminous infrared galaxies, or as they are designed by their acronym ULERGs, which have infrared luminosities in excess of 10 to the 11 solar luminosities, are the perfect laboratories to study the triggering and dust-obscured starbursts via galaxy merger, and to understand the convolution of star formation and supermassive black hole accretion across cosmic time. LERGs and ULERGs were an unknown galaxy population back up to the 60s, when they were discovered in the first observations that were done in the far infrared part of the electromagnetic spectrum. And there they were detected by being extremely bright in the infrared, so bright that they emit most of their energy in between the mid and the far infrared. Here, as you can see, like their luminosities are in excess of more than 2 orders of magnitude of what you can see in the UV and optical. And the reason for this was not known, this mechanism was not known until the 70s, when it was discovered that it was actually because these galaxies contain large amount of dust that obscure the central energy sources, both the star formation and the black hole accretion. And this dust absorbs all this UV radiation and optical radiation and remits it as a thermal black body in the far infrared. Later on, thanks to Spitzer, we learned that LERGs and ULERGs are not important only in the nearby universe, but also at high redshifts, where they actually start to dominate the contribution to the total obscure star formation rate in the universe at redshift larger than 0.5 or 10, where LERGs and ULERGs, they contribute most to the star formation rate density at those redshifts. But ULERGs and LERGs are important not only on their own right, but also when one thinks about them in terms, puts them in cosmological context, right? Because the current paradigm that we have for the universe, which is like the formation of a structure in the universe, is lambda CDM. And lambda CDM predicts a distribution of dark matter halos that once one accounts for the cosmic baryon fraction, predicts a distribution of a number of galaxies with a given stellar mass that is very different from what we actually observe, both at low masses and at high masses, right? There are many less galaxies at both low mass and high mass with respect to the predictions from lambda CDM. So this means that either lambda CDM is wrong, and well, it's very unlikely, but there are people trying to test for that. Or it means that there is a mechanism or a number of mechanisms that are there and prevent the galaxies from forming too many stars. What we think now is that at the low mass end, this may be basically turbulence-driven star formation feedback, which makes the gas in galaxies be very turbulent, agitated, and this delays star formation in a way that galaxies form stars less efficiently, and then they have less masses for what they were expected to be at their given time. In the high mass end, on the other hand, it is believed now that the mechanism, the front-runner mechanism for explaining this dearth of galaxies at the highest masses is basically quasar or AGN feedback, in particular momentum-driven feedback. And I want to focus on that now because right now we have like a well-developed paradigm for how quasars come to be for the origin of quasars in the local universe. I don't know if you have seen this figure before, but it summarized very nicely the mechanism that is at the foundation of the origin of quasars. And its simulations and observations tell us that quasars form out of the merger of two or more massive gas-rich galaxies, right? And well, the story goes as the interaction itself provokes the loss of angular momentum of the material of the baryons in the galaxies that are interacting, which basically are funnel all this material to the center of the two galaxies first, and then to the center of the system when the galaxies has coalesced, right? Because of this transport of gas to the center of the galaxies, there is a large column densities that of dust that obscure the star formation and the black hole accretion. So we see them in the infrared. Once the mostly black hole accretion kicks in and feedback starts to ignite at the core of these galaxies, the remaining gas and dust that was not used in the formation of the stars or accreted to the supermassive black hole, then is blown out from the system, and then these obscured quasars that are detected in this very short time scale, suddenly they are unobscured, and we can observe them in the optical directly. We can see the accretion disk of this, right? And in this process of blowing out the material from the center of these galaxies, from the central kiloparsec, we think that also basically is a process that also quenches star formation in the host, such that there are no more stars formed, and the galaxy decay into first a K plus A, and then a dead elliptical, basically. So we know that, and there is a lot of evidence and simulations that support this scenario in the local universe, right? But we don't know if this paradigm holds for high-redshift galaxies, right? Because we know that galaxies at high redshifts, basically at cosmic noon, at redshifts between 1 and 3, and even beyond, at the peak of the activity, star formation activity of black hole accretion in the universe, when it was at this peak, we know that galaxies have typical interstellar medium conditions that are very different from what we observed in nearby galaxies, right? And this is synthesized in a number of very well-known figures relating indicating that, for example, star formation in normal galaxies was much larger at early epochs, right? It increases by an order of magnitude of more from the local universe up to redshift 1 and 2, right? So this is a significant increase in the average star formation rate. And part of this can be explained by a simultaneous increase of the molecular gas content in these galaxies, which also increases as we move to earlier epochs, right, up to redshift 1 and 2. This increase is not an order of magnitude, but is a factor of 5. So it cannot completely explain the increase in the star formation rate in galaxies. But I will explain more later. We also know that galaxies at higher redshifts have larger molecular or interstellar medium gas fractions, both because there is an increase in the total molecular gas content, and also because galaxies have formed less of their stars at early epochs. We see that at redshift beyond 2, the gas fractions are in excess of 70%. And another reason why we see that may explain this increase in the star formation rate up to redshift 2 is because stars form more efficiently back at early epochs. This is seen in this figure. Well, this is the inverse of the star formation efficiency is the depletion time scales, the time that it takes to deplete the molecular reservoir of a galaxy given the current star formation rate, right? So as you can see here, the depletion time scales are shorter, which means that the efficiency out of which, like how many stars are formed out of per unit molecular gas is higher. I mean, depletion time is shorter, which is a factor of 3, which helps to explain why the star formation rate is so high at the early epochs. And finally, another hint on the reason why galaxies have their interstellar medium so different at high redshift is because also if you take into account all these trends, you realize that there is also a need for accretion at higher redshift, larger amounts of circumgalactic gas need to be accreted to the galaxies in order to sustain these very high star formation rates. So as you can see here, is like this is a compendium of evidence that suggests that at high redshift, both the internal properties of galaxies as well as their environment and their galactic medium were very different. So, I mean, you can ask the question, well, is then the paradigm of quasars that I explained just before valid at high redshift? So this is what I'm going to try to convince you and talk about during this first part of the talk. And in doing so, I'm going to talk about this special population of galaxies called hot dust obscure galaxies, or hot dogs for short. This is a population of galaxies that were discovered by the WISE space telescope. WISE was a all-sky survey that imaged the entire sky in 4 bands: W1, W2, 3, and 4. The W1 and W2 are near-infrared bands at 3 and 4 micron, and W3 and W4 are 2 bands at 12 and 24 microns. So hot dogs were selected such that they were very bright, very well detected, high signal to noise in W3 and W4 in the mid-infrared, and then not detected at all or very, very faint in W1 and W2. And this selection basically selects around 2,000, there are 2,000 of such objects in the entire sky. And as you see here, the redshift distribution of these hot dogs ranges between around 2 and 3, with a tail that extends up to redshift 3.5, with a very special case here of the most distant hot dog and actually most luminous galaxy that we know of, which is a redshift 4.6, and I will talk about it later if I have time. So in terms of the luminosity of these galaxies, we got Herschel photometry for more than 200 hot dogs. And even just by looking at the SEDs, not even by fitting them, but just like joining the points, the photometric points in the SED, you realize that the luminosities, the volumetric luminosities are in excess of 10 to the 13 solar luminosities, right? So these are very infrared dominated galaxies. And out of those, we know that around 10% are in excess of volumetric luminosities of 10 to the 14 solar luminosities. So we are talking about the most, or among sources that are among the most luminous objects that we can see in the extragalactic sky. And as you can see, by selection, as the most luminous sources tend to be at the highest redshift, with all these in excess of 10 to the 14 solar luminosities being all at redshifts larger than 2.5. So how the SED of hot dogs look? This is here, show the normalized nu. This is the running median of all the hot dogs, which you see that they are plotted here in the background. The SED of all of them are very similar to each other, right? So, and you see when you compare it with SEDs of other quasars, for example, at the lower redshifts, if you compare them to type 1 and type 2 quasars, you see that these quasars have an excess in the UV and the optical light, right? And you need basically an extra osculation of up to 6 magnitudes in order to bring back all this to resemble the huge fall in luminosity that you observe in hot dogs from the mid-infrared down to the near-infrared rest frame around 1 micron. And because this dominance of the central supermassive black hole and in the emission in the near-infrared, it's very difficult to observe their host galaxies, because you can only see them in the UV optical, and it's very difficult to obtain their stellar masses, because we cannot model really, or we have to be very very precise in modeling the all stellar populations, right? And well, they are called hot dogs because not only they need a number of black bodies to fit their SEDs in the far infrared, where the coldest black body is around 60K, but also in the mid-infrared, where gas components of up to almost 500K are needed, and that's why they get the adjective of hot from hot gas obscure galaxies. So there have been several pilot surveys that trying to measure the black hole masses of these galaxies using optical and UV spectroscopy from a number of large telescopes. And what is seen is that the black hole masses are in the order of 10 to the 9 solar masses, which are very high mass for relatively high mass for the redshift where they are located, which is redshift 2 to 3, right? So. But even with these large black hole masses, their luminosities are so large that basically the Eddington ratios that we get are close to unity. So they are radiating at almost the maximum that that a black hole can radiate before the luminosity exceeds the in pressure the gravity, right? So this is how hot dogs compare with other quasars at other redshifts. This is the blue cloud, this SDSS quasars at redshift 2, and these colored, other colored data points are quasars or submillimeter galaxies or dust obscure galaxies, not hot dust obscure galaxies, at other redshifts. And yes, you can see hot dogs occupy the upper envelope of the population with the highest Eddington ratios at a given black hole mass. And this is the special case of 2246, which has an Eddington ratio, is an outlier Eddington ratio of around 3. Also, in the optical, we detect very broad and blue shifted outflows in both the hydrogen recombination lines, H alpha, H beta, and also in oxygen 3. And we believe that these powerful outflows are caused by the large luminosities and Eddington ratios that we see in these supermassive black holes. So in order to not only study the characteristics of the black hole, but to also investigate the properties of the interstellar medium of the host galaxies, right? We carried out a multi-cycle ALMA campaign aimed at studying the ionized gas in the most luminous hot dogs. Angular resolutions were around 0.2, which translate at the distance of the sample of 1 to 2 kiloparsecs. The sample was small, but it was representative of the most luminous hot dogs. So here we are talking about volumetric luminosity, so from 1 to 3.5 times 10 to the 14 solar luminosity. So very luminous as some of the most luminous clusters of galaxies that we see today. So these hot dogs were at redshifts between 3 and 4.6. And as I mentioned before, 2246 is the most luminous galaxy known that it was the one first observed. C+ was the line of choice that we target. This is a fine structure line in the far infrared at 158 micron, and we detect it together with its underlying dust continuum emission. For those of you that don't know much about this line, I can tell you there is an excellent tracer of the interstellar medium conditions, as well as the dynamic in galaxies, because it arises from a large number of phases of the interstellar medium, both from the ionized gas, from the neutral gas, and from the molecular gas, right? And it's a line that is, well, it's a species that's it's very easy to ionize, and also this transition has a very low equivalent temperature, so it's very easy to excite, collisionally excite with the gas around. So results from this study, basically, to put it in context with the picture that I gave you in the beginning, in the question of whether these high redshift obscure quasars fit into the picture of the origin of quasars that we have in the local universe, right? In the nearby universe, we know that most of the most luminous quasars happen to be once the two galaxies have coalesced, right? And you have very compact morphologies and very disturbed kinematics in the system. But to our surprise, what we see in hot dogs is a variety of velocity fields, right? We see from sources that are barely rotating, that they have very soft velocity gradients, to others that show very well-ordered kinematics, resembling disks, maybe thick disks, not thin disks. Others that just look like they are rotating, and okay, one that shows a very complicated kinematic profile. If you go into the data cube of this galaxy, is a mess because you have a lot of components appear here and there in velocity. So this one, it looks like we are witnessing like a multiple merger in the system. So we have galaxies with complex kinematics indicating the presence of multiple components, right? So it's a variety of kinematics in terms of velocities, but all of them show systematically very high velocity dispersions. All the hot dogs that we detect have a full width at max of the line in excess of 500 kilometers per second. So this indicates very disturbed and turbulent interstellar medium, which one would expect that is associated to the powerful AGN feedback, but in cases like this, it can be also caused by the interaction and the turbulent heating associated to the dynamical friction of the gas and the dissipated nature of the gas in this specific source, right? And to put a little bit in context, this velocity dispersions with other populations of galaxies at high redshift, we can see here that hot dogs are in red, right? And this is distribution of hot dogs. And in pink, you can see the distribution of normal star-forming galaxies at redshifts 4 to 6. You can see that they peak around 200 to 300 kilometers per second, and even other quasar populations at various redshifts from 5 to 6 and 7. We see how the distributions peak around 400 kilometers per second, with some extension in excess of some sources in excess of 500 kilometers per second. But you can see any test will tell you that likely none of these populations come from the same parent distribution as hot dogs, right? In terms of the black hole masses, for the two sources for which we managed to perform a proper kinematic modeling, we found dynamical masses that, when compared with the black hole masses, they put these two hot dogs not in a special place in the parameter space of this diagram. This galaxy here, the black hole mass is very uncertain because apparently the Eddington ratio for this galaxy is very small, but if you expect that it's as high as the rest of the population, it would put the data point over here, together with other populations of galaxies at other redshifts. So it looks like, in terms of black hole masses and dynamical masses, hot dogs are not in a particular extreme place in the parameter space. What it is surprising, though, is that if you expect that there is a coevolution of the star formation and the black hole accretion, and these sources are accreting at high rates because they are very luminous and they have high Eddington ratios, you would also expect that the host galaxies would be forming stars at higher rates, right? But what we see here is that they basically spread all over in this diagram, where this is, I don't know if you're familiar with the main sequence of star-forming galaxies, where at a given cosmic epoch, you have a very well-defined population of galaxies and a correlation between the star formation rate and their stellar mass, right? And these are delineated by these lines at different redshifts. And what you can see is that hot dogs do not fall systematically above this main sequence of galaxies. Some of them, they look like they are above, but the uncertainties are big because, as I mentioned before, it's very difficult to estimate the stellar masses of these galaxies. And also the star formation rates come from a number of scaling relations in which you have to subtract the contribution from the emission from the AGN, so it becomes very uncertain. But as a population in itself, it looks like they are not systematically above, which is surprising, right? And I wanted to talk a little bit, a parenthesis here about these particular galaxies, galaxy 2246, because it's a very interesting case to study the environment of luminous galaxies at high redshift. Because there is statistical evidence that hot dogs live in dense environments, but this evidence comes from the stacking of fields, both in the submillimeter and the near infrared. but there hasn't been any hard evidence on individual sources which contains a large number of companion galaxies, right? But ALMA allows to search for C+ emission line objects at the same redshifts and continuum detections within the field of view. And in fact, for this particular source, 2246, we detected 3 companions. Here, one very close to the central hot dot at 1 arcsecond, which equates to 6 kiloparsecs, more or less. Another one here at 35 kiloparsec, and another here that we missed in the beginning because it's the very edge of the spectral window, but that we recover in a blind search of the cube. And then later we corroborated by taking a Keck spectrum and we detected Lyman alpha emission exactly right at this spot. And if you see the HST image, this is a res frame far UV, res frame far UV. You see that the system is has a lot of knots and structure, suggesting that there is a lot of things going on in there, right? You have sources that you detect both with ALMA and with HST. Some of them are not that clear. Some of them are very detected with HST. Some other are detected with HST and not ALMA. So there is probably a very complex dynamics. However, the fact that we detected companions close to these quasars, it was not new at the time because these other studies had shown already that at even higher redshift, at redshift larger than 6 or redshift 5, you have a number of quasars were showing companion galaxies very close to in projecting distance to the central quasar, closer than 600 kiloparsecs, and at very close also in velocity as well. But in our quest to to study the interstellar medium of this particular galaxy, we wanted to observe this nitrogen 2 line at 200 micron, more or less. And this line is very faint. It's a very faint line, and we wanted to integrate a lot in order to detect it, to detect not only the emission line but the continuum, to see what was going on in the center of the not only in the center of the hot dog, but in the wanted to detect also the companions at a greater significance. And what was our surprise, that we not only detected the companions, but we also detected this very large structure, which resembles like a tidal streamer, which is it was the first time that such a structure was detected in a quasar at such higher redshift, right? And one of the most interesting aspects of this study was that if you actually calculate the amount of dust and gas that is surrounding the central quasar, is as much as what the host galaxy has, right? And if you assume make some assumptions about the time scales over which this material can be accreted to the central supermassive black hole, you realize that is enough to sustain the star formation rate that we see in the host galaxy and the accretion, obviously, to the supermassive black hole for several hundred mega years, right? So it looks like even at these early epochs, the feeding of companion galaxies may be an important mechanism on how to create a hot dog, and not just possibly accretion from pristine gas from the cosmic web. Right? So coming back to the question well, what about the extremely luminous hot dog phase? Is it a single continuous event like the established paradigm of the triggering of the Euler phenomenon at low redshift? So let's look at the evidence. And The evidence tells us that there is a variety of morphologies, NC plus and dust continuum, always high velocity dispersions, but we also detect very distinct and diverse dynamical states, rotating disk, complex kinematics, slow rotation. We also know that, at least in this case, there are a significant number of companion galaxies. I mean, we had detected this, but there are others for which we don't have redshift because it does continue. And there are a number of extended structures, right? So this is something that you don't see in advanced mergers in the local universe. So extremely luminous hot dogs don't seem to be systematically at the latest stage of a major merger interaction, right? So this, at least this indirect evidence for a scenario in which the extremely luminous hot dog phase could be actually recurrent or episodic, right? Because you see a diversity in kinematics and a diversity of properties in the sample. A small sample, but it hints at this phase could be episodic yet chaotic, obviously, because probably there is a chaotic infall from nearby sources. But one interesting point of this is that, as I mentioned before, the black hole masses of these hot dogs are already very high. Actually, they are so high that they are only one Eddington or saltpeter time away from actually reaching the black hole masses of the most massive galaxies that we see today. So they only have 40 mega years radiating at these luminosities and with these Eddington ratios to reach that mass. So if the hot dog phase is to be episodic or recurrent, it needs to be very, very short, right? It needs to, these 40 mega years need to be split in many few mega year events or lower than a mega year event in order to be consistent with this picture. And this is actually consistent with previous studies reporting on the flickering time of AGN. Okay. For this. So, okay. Conclusions for this part of the talk. Hot dogs are a population of galaxies located at redshift larger than 1 up to 4.6, very luminous, very hot, show very hot dust components. They show a variety of kinematic properties, high velocity dispersions, turbulent ISM. The black hole masses are normal compared with other high redshift quasar populations, and the galaxy hosts don't seem to be far away from the main sequence. The important thing here is that the hot dogs fit into the paradigm of galaxy evolution. Well, this is the question, and we know that the ALMA results suggest that this may not be the case, and that this phase in galaxy evolution at this redshift may be recurrent. Right? And in the last minutes of the talk, I wanted to talk about a little bit of the most luminous galaxies that we know, but now in a different context, in the local universe. These are not only the most luminous galaxies that we know, but they are a distribution of, they have a distribution of infrared luminosities. And to do, for this part of the talk, I will be discussing results from the Great Observatory's All-Sky Lurch Survey, or GOLS for short. GOLS is a complete galaxy sample containing the 202 systems of infrared galaxies detected by the IRAS telescope. They are composed of 290 individual galaxies. And as you can see here, they span, in this case, the entire merger sequence. We have not only, like later stage mergers, but we have also galaxies that look isolated, early interacting stages, all the way to the moment of coalescence, right? And in this case, we have a range of star formation rates that they span from normal star forming galaxies like Milky Way up to starbursting sources. And we perform a survey with Herschel packs, and we obtain a spectroscopy for 3 of the main fine structure emission lines. Again, C+, traces a number of phases of an interstellar medium, but also oxygen-3, this traces ionized gas, and oxygen-1, which traces photodissociation regions. Right, and as you can see here, there is a number of profiles also resembling or showing the variety of kinematics that you have from this galaxy population, which are from isolated galaxies to latest measures. And one of the questions that have been there for the last decades in terms of these emission lines that we observe in the far infrared is that in all of them, we observe what is called a deficit of these lines when you compare them with the total infrared luminosity of the system. And we see that at the highest luminosity surface densities, the lines stop being efficient in cooling the gas with respect to the dust cooling, right? So you have a bending of this ratio to higher luminosities. What we discovered in this study is that it's actually this is caused by a combination of an increase in the radiation field in galaxies, combined with an increase in the dust to gas opacity and the dust temperature of the dust, which drives up the infrared luminosity much more than the increase in the cooling of the emission lines. We also saw that the spread in this relation is caused by the contribution of the PDR regime that is traced by C+ with respect to the total emission of this line. Basically, we see that, for example, the Milky Way here have a contribution from PDR regions, from active star-forming regions of around 50–60%, and LERGs have a much larger contribution from PDR, from active star-forming regions. C+ can not only be explained within the PDR context, but also in the context of shocks. Actually, this is the Stefan Quintet system. I don't know if you have seen the latest JWST press releases, but there is an updated picture of this multiple merger system. The thing to focus here is that if you take a look at the interface region and the overlapping region, and you plot again the emission of the line over the far infrared, these are outliers in that relation, and this is because in this region there is a shock gas which excites the line and makes it to have an excess with respect to the cooling that is done through the dust. Within the PDR paradigm, we can actually model the emission of these lines. And what we see is that as you move to higher luminosities, you have an increase in the interstellar radiation field. I mean, when these models, what gives you is as an output is the interstellar radiation field intensity and the density of your molecular cloud. And as you see, as you move to higher luminosities, the interstellar radiation field goes up. Also, we see that as the starbursting region is smaller, the filling fraction of these star-forming clumps is larger. This is synthesized basically in this figure over here, that actually is critical because it puts in context two quantities that are related to the local conditions of the star-forming regions locally, right, on parsec scales, which is the density of the molecular cloud and the radiation field that is seen, with two quantities that relate or are measured in terms of the integrated emission of galaxies, which is the infrared luminosity and the overall size of the star-forming regions. And what we can see is that there are two regimes below around 3 or 5 times 10⁻⁻10 solar luminosities per kiloparsec. Below that, as we move into high luminosity surface brightness, we don't see a change in the properties of the local star-forming regions, just an increase in the filling factor, right? You put more star-forming regions in the same area, you get more luminosity per unit area, but you don't change the. But above this threshold, you have an increase and a change in the properties of the star-forming regions. So this is a transition that it may be explained actually because if you look at the nature of these sources over here, not all of them are interacting galaxies, but most of the interacting galaxies are in this area here. So this could be the mechanism that put in connection or makes the connection between the small scales and the large scales. And to finish, I have a couple of thoughts. So you can ask, okay, well, this is the mechanism that that may be behind the scenes, right? But what is the actual observable that I can associate to it, or how can I really connect? So I think the answer is in the star-forming clumps that we detect in these galaxies. When we look at these galaxies with higher angular resolution, we see that most of the star-forming regions, that we see in them, at low mass, this is the number of regions per unit mass, stellar mass beam. At low mass, they are very similar to other normal star-forming galaxies or interacting systems that are less luminous, but there is a much larger number of massive clumps at the highest massive beams. Not only there are more massive clusters, but those clusters also have higher star formation rates, right? So this is seen here compared with more normal star forming galaxies, and this has been seen both from star formation rates calculated from thermal radio up to, and also with hydrogen recombination rates. And the last plot is basically, it's very interesting because it looks like the interaction process is making these galaxies to have more massive and clumps and more star-forming clumps, but it also looks like that it's also destroying them at a higher rate, right? When you see the number of clumps or number of star-forming regions as a function of their age, you see that there are many less clumps in luminous infrared galaxies at a given time than in normal star-forming galaxies, right? So the interaction process is both creating clumps, more massive clumps, more star-forming, but also destroying them at a higher rates. So it's like the dynamical scales, the duty cycle of the creation and destruction of these clumps is high. And this is just like you can see here that there are 2 points that we couldn't be sure about because these are very, very young star-forming regions, and we didn't detect them with HST. So because we were not sure, they were very uncertain, so we were not sure about, we fitted only this power law. But now with the preliminary results from JWST, we actually detect a population of heavily obscure clumps, very, very young, that we didn't see before, actually. And they are very young, less than 5 megayears. And then, as you can see here, they are very obscure. They require obscurations of larger than the AV of 10. And with that, we have been able to update these 2 points, which now actually agree very well with what we had obtained with HST. And I don't know if I can, it's up to you. If you're bored, but basically, very quickly. Well, or actually, better leave time for questions. You can see the conclusions here. Thank you. So, good questions.
So you said the C+C2 lines are very important for the mechanics. So could there be sort of like outliers where you don't see these lines and they could be classified as normal? And if so, which lines could you look at?
The selection of hot dogs is not based on line emission, it's based on basically dust continuum to be able to see a very hot dust component that dominates the spectral energy distribution down to few microns per frame, right? So what we think of the SEDs of hot dogs is that they follow a power law distribution, and they are detected this way from an all sky survey. In terms of the C+ line, I forgot to tell you, I didn't have time, but from the 7 hot dogs, we detected 4. But we know that 2, we had missed the line, and this is for another talk. It looks like the systemic redshifts that we get, or the redshift that we get from the optical and res UV emission lines from Lyman alpha, for example, are systematically blue shifted with respect to the systemic redshift that we detect from C+ or any other far infrared line. So 2 of them, we think we missed them. Like basically they fall outside of the spectral window because we later got CO observations for some of these objects, and actually we detected that they were redshifted like hundreds, if not thousands of kilometers per second. So C+, to answer your question, is not fundamental for the selection of hot dogs, but is a very versatile line. Let's say it's like a workhorse to detect not only hot dogs, but basically with ALMA, any galaxy at high redshift, it will be targeted with C+ first, and then followed up with other lines, because it's, as I mentioned before, it's very easy to excite. And there is a number of mechanisms that can make it very luminous. It can account for almost 1% of the luminosity, of the bolometric luminosity of galaxies, just in one line.
More questions?
Yeah, in the high redshift thing, I mean, I don't know if I'm speculating, but maybe you can help me. So it seems like at this high redshift, you find already in the very high redshift one, you're showing how you are acquiring already dust from the companion galaxies, right? And you're surprised that this happens already at this high redshift. And then recently with this JWST that they're finding galaxies at this super high redshift. So my question is, do you think star formation or the whole galaxy formation starts much earlier than maybe what we had thought? Is that possible, or?
Well, we were, I think, before JWST, the highest spectroscopically confirmed galaxy that we knew of was actually confirmed by ALMA. It was a redshift almost 9, basically. detected in oxygen 3, 88 micron. Beyond that, honestly, I'm not sure how reliable are the photometric redshifts that are we getting so far of from JWST because of calibration issues. I guess you have seen the new revised redshift for some of the galaxies. It depends on the number. Always depends on the number. If we detect many more than predicted at redshift larger than 10, then maybe yes, there is something that we don't understand about how the first galaxies were formed. Definitely, now it's interesting because with JWST we are detected well into the epoch of reionization, right? Reionization finished, we believe, at redshift 6, right? And it started at redshift 15 or so. Redshift 3 and 4 now is intermediate redshift, right? So it's a time where the universe was already ramping up to the peak of activity, almost. So it's passed well beyond the early stage, the early cosmic noon. So I don't know if I answered your question, but it depends on the numbers that we will get during the next months.
But what you were showing for this high redshift galaxy, is this also, I mean, that you expect it to happen actually later, right? So what I'm saying is that also something related to that it gets shifted to earlier times, or it was just because we were not able to see it before?
My guess is that because we couldn't see them before, right? But for now, I mean, most of the galaxies that we know of that are beyond redshift 6, 7, most of them are quasars, right? So it's a very biased view of the universe. High redshift galaxies where we see and resolve structure are up to redshift 6, something like that, 7. There are very, very few that are beyond that. So we still have a very not complete picture of how galaxies in a sense are formed, and particularly their supermassive black holes.
So it's almost time, it's practically time. So if there's any quick questions, do we have time for that? No, in that case, just we thank our speaker again.
If you enjoyed the video, like and subscribe.